guys, this is Vladimir from Mobatec. Welcome to video help of the third exercise of Mobatec Modeler Introduction course. While this is the third exercise of the course, it is the first model developer exercise. Before watching this video, I strongly recommend you to read the text of the entire exercise so that you're able to follow this video successfully. Let's start with the exercise. Exercise name is Modeling and Simulation of a Buffer Tank. So this is the first model developer exercise, and by the end of this exercise you will know how to build a model from scratch, how to write equations and add them to the model, how to monitor variable and parameter values using variable and parameter tables, and how to add parameter displays and filled rectangle displays. In section 1.2 we have a model description. Topologically speaking, this model has three systems and two connections. We have one battery limit system, inlet system, we have one capacity system, which is the tank system, and one battery limit system, which is the sink. We have inlet connection and outlet connection. So, we want to model a dynamic operation of a buffer tank. In the section 1.3, model assumptions are given. The tank is well steered, ideally mixed, which means that this is a lump parameter system. The operation of the tank is isothermal, which means that the temperature is constant and there is no energy balance. The tank contains single component in the liquid phase, water. The cross-section area is constant along the height of the tank. Now, before we take a look into the model equations, I would like to introduce you to Mobatec Modeler Handbook, reference manual for beginning and advanced users. This document is made in a form of slides, 2 slides per page, which are very easy to understand, very transparent and easy to use. If we scroll down to the first slide, we will see the contents of the handbook, and as you can see, there are 15 chapters which gradually explain you the model building process in Mobatec Modeler. For the third exercise of the course and the first model developer exercise, I strongly recommend you to go over the chapters 4, 5, 6 and 7 and learn about dynamics and model equations, first principle model building in Mobatec Modeler and mass balance formulation, degrees of freedom and initial conditions, running the simulation and viewing the results. In these chapters you will find a lot of knowledge on mathematical modeling in general and on dynamic modeling precisely, which will help you to boost your learning curve substantially. Let's go back to the exercise. Section 1.4 Model Equations. Here we can see all the model equations. We have 7 equations in total, 4 related to the capacity system, which is the tank model, and 3 related to the liquid lines, which are mass connections. First we have the buffer tank model equations. First equation is mass balance equation. This is an ordinary differential equation where time is only independent variable. That means that this is lump parameter system. We can see that mass accumulation over time equals to mass in minus mass out. Important thing to know is that mass balances are always automatically formed in Mobatec Modeler. In other words, Mobatec Modeler will always form the differential equations of your system without making mistake. What you have to do is to make and add to the system the algebraic equations, which are also called the constitutive equations of the system. To learn how balances are formed in Mobatec Modeler, go to Mobatec Modeler Handbook, Chapter 5, and find the mass balance generation slide. Here you can learn that you can have molar-based or mass-based balances in Mobatec Modeler. That is the decision that you will make. And once you have the system, like in this picture, if you have one connection coming and one connection going out, like in our exercise, and if you choose mass-based balance, as in our exercise, this equation will be formed automatically by the Mobatec Modeler. So, once you make the inlet connection to the system, and connection does not have to contain any equations, the first part of the mass balance will form automatically. Once you connect the outlet connection from the system, the second part of the mass balance equation will be added automatically as well. If you add one more inlet connection, you will see that automatically one more term will be added to the mass balance. One more term with a positive sign because it is inlet. And if you add one more outlet connection, one more term with a negative sign will be automatically added to the mass balance. Important thing to understand is that the balance equations will always be written in vector implicit form, and these brackets, square brackets, which are empty, are the sign of that, which means if you have n species, you will have one equation for species 1, 1, 1, then for the second species it will be 2, 2, 2, and for the nth species will be accumulation of mass of the nth species coming in minus nth species coming out. So the balance is automatically made from 1 to n species. And is represented in one equation which looks like this in the vector implicit form. Once that mass balance is formed in the system will ask for the presence of Fm vector or Fn vector if you chose molar-based balance of these variables in the connections that are connected to the system, as the system uses those variables to define the mass balance. So you will have to define equations with these variables in all connections connected to the system. Now let's go back to exercise. So we have explained the mass balance equation, then we have the buffer cross-section area equation, then we have total mass holdup equation and liquid level equation. In the liquid lines equation we have inlet mass flow rate equation, then we have inlet component mass flow rate, this is the one that we need to form the mass balance, and the outlet component mass flow rate equation. Also, this is the equation that we need to form the mass balance. In the section 1.5, we have all the model parameters given by the symbol, description, model object, whether they are in the system, inlet or outlet connection, and their units. And in the section 1.6, we have all the variables of the model given in the same table. Then we go to the section 1.7, which is the actual exercise, things to do. Task number 1, create a new model. Open the Mobatec modeler and go to File, New Model, or go to Basic Commands tab and click the button Create New Model, or go to this icon in the toolbar, New Model. You can resize the model or maximize the model window. I will immediately save the model, so choose any other location than Mobatec modeler root file. So I'll go to desktop and type buffer tank. Save, and your model is now saved with the name buffer tank. Task number 2, building model physical topology. As we are building model from scratch, we will also use systems and connections from scratch. To insert systems from scratch, press Insert New Objects button, the Basic Commands tab. You can find the very same button here in the toolbar, or go to Property Browser, Insert Objects, Systems from Scratch. Here, under the type, you can choose which type of the system you want to add, and here you can choose whether you want to have molar-based or mass-based mass balance. Moles are selected by default, but in our exercise we will use mass-based balance, so choose mass. We have 3 systems, one inlet battery limit and one sink battery limit, and one capacity, which is the buffer tank. So let's first add inlet and sink battery limits. So just choose battery limit and click. You will see that these systems are orange by default. And now choose capacity system and add that system for the buffer tank, as capacity system can for mass balances. Go right mouse click or exit on your keyboard to exit adding more systems. You can also use the shortcut to access the systems from the scratch property browser tab, and that is to hold shift and press S, like capital S, and you will access the systems from the scratch tab. So as we learned in previous exercise, just S, like small s, will access the regular library, which is, by the way, very rich with all kind of models. And by pressing Shift S, you will access systems from scratch library. Now let's add connections from scratch. Go to Property Browser, Insert Objects, and find Connections from Scratch. Here you can choose which type of connection you want to add. We want to add mass connection, and we will choose unidirectional mass. Unidirectional means that the species will propagate only in the way where the connection is headed. So choose unidirectional mass and click on the system 1 battery limit, and then click on the capacity system, then click again, just keep adding from the capacity to the second battery limit system. Go right click or exit to exit adding more connections. We can now rearrange the layout of our model. Let's move this a bit here, and let's move this a bit down, like this, and we are good to go. Let's continue. Task number 3, adding icons to systems and connections. Go to General and choose Icons subdirectory. Icons tab will open. In the Plant Icons box, you will see that there is nothing. In the Available Icons box, choose Exercise Icons folder, select Buffer Tank, and press Add Plant Icon. Buffer Tank will appear in the Plant Icons. Do the same for the Liquid Source, Liquid Sink, and Valve icon. Now we have added all the icons to our. Now let's add the icons to all model objects. Select the inlet battery limit and go to Graphics tab. In the Plant Icons box, you'll be able to see the icons that we already added. Select the Liquid Source icon and press Change Icon button. You can see that the icon is added. Use your mouse to resize the icon. Select the Buffer Tank Capacity System. Again, go to Graphics tab, select Buffer Tank icon and press Change Icon button. You can also add the icon by doing a double left click on the icon here like this. As you can see, the icon is added. Let's increase the much. Let's do something like this. Select the Sync battery limit, go and add the Sync icon. Let's resize it a bit more. Okay, this will be less. Great. Select the inlet connection, go to Graphics tab and choose Icons sub-tab, and here choose Valve icon. You can also do double click here as well. So now we have added all the icons to our model. Now let's rename our model objects. Select the inlet battery limit, go right click, go rename, or just press F2 on your keyboard. Let's change the name to Source. Select Buffer Tank, change its name to Buffer Tank. Make sure not to have empty spaces, so if I do this, you can see that there is a message saying illegal characters. So do it together or with the underscore or something else. Let's change the name of the sink to sink. Inlet connection to flow in. It will be short for F in. The name here, F out. Rename. Okay. Now we should rearrange the layout of the model a bit further. Select the connection, go right click, set graphical connection offsets, choose better point, right click to exit, move this connection here, this is better. You can also easily adjust the position of the label. If you select the systems, any system, you can go to graphics tab, and here you can see the position of the label under, above in the system, or hide. And you can also use the shortcuts. So to hide, use 6 on your keyboard, below use 7, above use 8, and in the middle use 9. So we will use below. For the sync is already below, we just have to do this. Very good. For the buffer tank, let's hide the name. For the connection, it is also, just go to attributes subtab of the graphics tab, and here you can find the position of the label as well, the same. Use the same shortcuts. So we want it on top, so we will use 8, and here let's leave it in the middle. Okay, let's continue. Task number 4, adding species to your model. We have already demonstrated this step in the second exercise. We will do it again. So go to General and choose Plant Species and Reactions. You can also access this tab if you press this button in the toolbar. As you can see, we can see that the Plant Species box is empty, so press the Find Plant Species button. Here, choose Default Database to access all the species from the database. Find water, select water, press Add button, press OK button. Now we can see that we have added species to the model. Now let's inject water to our source. So select Source, go to Species Topology, and press Set Injected Species. We can see that there is still no species in the system, so we have to inject species. Set Injected Species, choose water, press Add, and press OK. Now we can see that water is in the system, and these 3 stars signify that water is injected in this system. If we go further down stream, we will see that water is present in the connection, systems, outlet connection, and sync. Let's continue. Task number 5, writing and adding equations in Mobatec modeler. As we already explained, mass balances are formed automatically once we connect mass connections to capacity systems. We have connected the inlet and the outlet mass connection to a buffer tank capacity system. So if we select the buffer tank capacity system and go to equations, here you will see automatically formed mass balance. So we can see that the species mass change over time is equal to the species coming in minus the species mass coming out. And as we already said, the mass balances are always in vector form with these square brackets which are empty. Even if we have one species, this is the shape of the mass balance. In a single component case like this one, we will just state, once we initialize the buffer tank system, that this is 100% water, and then the mass balance will be only accounted for water. Now let's start adding the equations. If we go back to the exercise chapter 5, here you can see all the model equations. Here they're written in the shape they should be written in Mobatec modeler. As you can see, the syntax is very simple, and by the end of this course you will have no problem writing any equations that you want in Mobatec Modeler. So let's first add the inlet connection equations. We need to add two equations to inlet mass connection. Inlet mass flow rate, Fin equals alpha, which is the valve position, times Fn, which is a parameter and it is user defined. And the inlet component mass flow rate, which is component flow rate, Fn with the square brackets, which are empty, equals Fin, which is inlet mass flow rate, times Xm of the component, and Xm is the fraction or the content of the component in the inlet mass flow rate. In our case, this will be 1. As we explained earlier, in mass connections, we have to calculate the component mass flow rate variable, as this variable is going to be used in the automatically formed mass balance in the capacity systems. Now let's add these equations to the inlet mass connection. Select the active point of the inlet mass connection and go to Equations tab. Here you will see that in the equations there is no equations defined on this level. Press Define Equations button. Here we can see the three subtabs: Define Equations, Equation Sorting and Referencing, Constant, Parameter and Variable Values tab. We will go through each of these tabs, but first let's get ourselves familiar with the Define Equations tab. Here we can see at the very top Selected Database. We can see that Selected Database is default database. This is because once we added the species, we changed our model database to default database. Then in that process also the equations database was changed to default database. You can see that there are a lot of equations present in this database that you may use down the road to make your own models. But as we are going to make the model from the scratch, we will use our own equations. We will create our own equations. So change to buffer tank database. Now you can see that the database of equations is empty, as we haven't created any equation yet. Now let's create the equations for our inlet mass connection. Press Define New Equation button, and the Define New Equations tab will pop up. First we have the function box, and here we should type the equation. Fin equals alpha times Fm. Beneath we have the result log, and here you will get the messages if, for example, your equation function is not written correctly. For example, if I have not typed the multiplication sign, then we will get an error in equation, and @ sign is used to signify exact point where the error is. So here, if I type again multiplication or plus or minus depending on the equation, we will get no error. And here you also have the instructions on what to do. Enter a name, specify equation class, dimension, and give a function. We have given a function. We will give the name, so the name from the exercise. Also don't use empty spaces. For example, if I have empty space, then I'll get illegal character message. So use the underscore or something else to write the equation name correctly. Then we have description box. This is optional, and here you can enter the text to explain the equation. This is handy if some other team members will use the model so that they can understand the equations that you used. Then we have equation class, and the mass connection checkbox is checked as we are adding equations to mass connection. Equation class is actually equation categorization by the type of the model object. We will talk about this a bit later. Then we have dimension, which is determined automatically by the software checking your equation. As we can see, this equation is scalar, that's why scalar is marked. And here we have used variables. Software will display all used variables in this equation. If everything is OK, then the OK button should be available for you to press. Now we can see that we have added this equation to the database equations of our model. Let's now create the second equation. Again, press define new equation, the same process. Type the function of the equation, so fm square brackets equals fin times xm square brackets. So we have no errors. Type the name. Mass connection equation class is checked. The equation is vector, as we can see. Here are all the used variables. As you can see, fm with the square brackets is immediately recognized as component mass flow variable, as this is predefined variable in Mobatec modeler. Press OK. Okay, now we can see that we have added both equations for the inlet mass connection. Now just select the equation and press add button to add equation to the mass connection. Like this, and select the second one like this. We can see that the object equations are these equations. Press done. And now we can see in the equations tab that we have added both equations to the mass connection successfully. We can see that we have improper defined equations message with exclamation sign, and that is because we have 1, 2, 3, 4, 5 variables and only 2 equations, so the system is yet not well posed. We will get to this later. Now let's add equations to the buffer tank capacity system. Select the buffer tank system, go to equations tab and press define equations. Go define new equations. Type the first equation, area, so area equals to diameter squared times pi. This is how you define pi in Mobatec modeler. Over 4. Type the equation name. System equation class is checked by default as we are adding equations to a system. The dimension is color, as we can see, and use variables are a and d. Press OK. Now you can see that we have added area equation to the database equations of the model. Now let's add the other 2 equations. Go define new equation. Now we will add the equation for the total mass holdup. M equals sum of component mass. Equation name. Equation class is system. Equation is color. We have total mass holdup and component mass holdup, which is predefined variable in Mobatec modeler, and that's why it is recognized. Press OK. Again, press define new equation button. Now we will add liquid level equation. M equals rho, which is mass density, times area times liquid level. Enter equation name. Equation class is system. Equation dimension is color, and here we can see the variable used in this equation. Press OK. Now let's add the equations to the buffer tank system. Press done, and in the equations tab we can see that we have added the algebraic constitutive equations of the buffer tank system. Now let's add the last equation of the model to the outlet mass connection. Select the mass connection, go to equations, click define equations button. As we can see in the database equations, we can see the 2 equations that we have added to the inlet connection. They appear here as we are about to create or add equations to the mass connection. As these equations were marked equation class mass connection, they appear here, and we can reuse them in any mass connection in the model. Now click Define New Equations button, as we have to define new equation outlet component mass flow rate for the outlet connection. Fm equals beta, which is flow resistance parameter, times square root of liquid level in the tank. In order to use the liquid level variable, we have to type prefix or dot L. This prefix signifies that we are going to use the origin variable, as buffer tank is origin system of this connection. If we are about to use the target variable, the variable which is located in the target system, we would use tar.l. Enter the name. Equation class is mass connection. The equation is vector, as we can see. And here again we can see variables, so beta, component mass flow, which is recognized as it is predefined variable in Mobatec modeler, and software also recognizes the or prefix or dot prefix and knows that this is liquid level from the origin system of the connection. Press OK. Now add the equation to the outlet mass connection. Press Done. Now we are finished creating and adding equations to all model objects. Before we continue further, I would like to introduce you to the Main Editor tab. You can access it if you click this icon in the toolbar. You can also access it if you click button D on your keyboard, like this. Main Editor tab is like a control deck for your model. Here you have 6 tabs. The very first tab is the Equation tab. Here we can see all the equations that we have created and added to our model objects. Here you can choose to see whether you want to see equation names and equations, or only names or only equations. Anyhow, you can see all these equations, as here in the equation filter we have selected all equations. If we select mass connections only, we will see the equations which have mass connection equation class. If we select system equations, we will see the equations which have system equation class. Here you can change any equation. For example, if you want to change the cross-section area equation, just select the equation and press Edit Equation button. Then you can change the equation the way you like and press OK. Then the equation will be automatically changed everywhere where this equation was present, in all model objects. So you have to change it only once, and that is very convenient. What you could also do here is to create any new equation by pressing New Equation button. You will get Define New Equations tab, the very same tab, and you will create equations the very same way. The only difference is that now you have to select by yourself the equation class, as now you haven't selected any model object. So this is the other way to define all the equations. You could define them here and then just go and select model objects and choose the equation from the available equations that you have created, and then add them to your model objects. The second tab is Variables tab, and here you can see all the variables that are present in the model. The variables with a description are predefined variables in Mobatec modeler, and they are always present. The ones without the description are the variables that we have created while creating the equations. Now let's continue with the exercise, as we will use this tab to perform the next task. Task number 6. Declaring variable dimensions. Variable dimensions are very important in mathematical modeling in general, as if you don't keep your dimensions straight, you can easily end up with the factors 10 or 100 or 1000 or even more. and that can affect your result seriously. Keeping the unit straight is very easy in Mobatec Modeler, as each variable unit is defined only once and will remain the same throughout the entire model. So once that you have defined units of your variables, you don't have to worry about them anymore, and you can use those variables to define as much equations as you want. Units will remain consistent throughout the model. In table 3, we have all variables dimension declaration. First we have the variable name or symbols, then we have description, we have engineering unit, category unit, and upper and lower bounds. For the diameter, D, we have engineering unit meter, category unit length, and bounds from 0 to 100. Let's go to Mobatec Modeler, select D, press edit variable, the name type diameter. In unit category, select length, lower bound 0, upper bound 100. We can see after we have selected length that engineering unit was automatically set meter. Here you can put some description if you like, and then press OK. Now we can see that diameter has description and we have defined the bounds and the unit category. Do the same for all other variables. Now we have defined the units of all variables with defined category units. Beta is only variable without defined category units. If you have a variable like this, just select it, go edit variable, leave unit category undefined, and enter your own unit. Here is the name, and the lower bound is 0 and upper bound is 50, and press OK. Make sure to use correct units for these kind of variables. If for whatever reason you do not define your variable units, Mobatec Modeler will always use basic system international units, so kilograms per second for mass flow, kilograms per mass, meters per second for velocity, and so on. We will explore the rest of the tabs of main editor in some of the next tutorials. For now, let's continue. Task number 7. Sorting the equations. First question that we need to ask ourselves is, what is a well-posed system? Well-posed system is a system that is solvable and has the same number of variables and equations. If we have more variables than equations, then the system is not well-posed, and we need to turn some variables into parameters to make the system well-posed. Systems which have more variables than equations are called underspecified systems. That's why we have to turn some variables into parameters. On the other side, systems which have more equations than variables are called overspecified systems. Mobatec Modeler has developed equation sorting routine to help the user to make well-posed systems every time. If you check Mobatec Modeler Handbook, Chapter 6, Slide Degrees of Freedom 1, you will see the mathematical analysis of our very model. Here you can see that we have 13 variables in total and 7 equations in total. That means that we need to define 6 extra input specifications. In other words, we will define these variables as parameters and make our model well-posed. Going back to the model, let's start with the inlet connection. Select the inlet connection and go to Equations tab. Here we can see 2 equations which have, both of them have these 3 stars in front, which means that we have improper defined equations. Click Equation Sorting and Referencing button. And now Define Equations tab opens and you have Equation Sorting and Referencing tab open. Here we can see that we have 2 equations defined in this model object, And in the selectable box, we can see that we have in total 5 variables. These stars, as we already mentioned, signify that this system is, in this case, underspecified, as we have more variables than equations. So now we need to turn some variables into parameters. If we now take a look at a handbook, slide Degrees of Freedom 3a, we can see the analysis of inlet mass connection. We have 5 variables, we have 2 equations, so we need 3 more inputs. And from the exercise we know those are alpha, valve position, Fm, mass flow, set by the user, and Xm, which is a fraction of the species. Only thing that we have to do now is to select these 3 variables and turn them into constants, or parameters. Software will automatically move Fin, inlet mass flow, and Fm to the computed and known box, as now we will have 2 equations and 2 variables. And the system will be well posed and will produce singular solution. So let's do that. Select alpha, select Fm, and select Xm. As you can see, we have lost the stars here. Fin and Fm are moved to computed and known box, and we have the message that equation sorting and referencing is okay. Now let's move to the buffer time capacity system. Again, let's check the handbook. Slide Degrees of Freedom 3b. Here we have an analysis of buffer time capacity system. We have 6 variables and 4 equations. That means we need 2 extra inputs, and from the exercise we know those are diameter d and raw density of the fluid. Don't be confused, as mass balance equation is not shown in the object equations box. This is the case because a mass balance equation is generated automatically and is not added by the user. Also, the component flow rates Fm in and Fm out variables are not added to this list here, as they do not belong to the buffer time capacity system, but to the mass connections, the inlet and the outlet mass connections, and they're being calculated there. If we take a look here, we will see 3 equations, and 2 of them have stars in front, which means they cannot be calculated from the current setup of variables and parameters. Equation for the total mass holdup, M, can be calculated as it is being calculated from the component mass holdup. Component mass holdup is immediately moved to computed and known box, as this variable is going to be calculated from the inlet and outlet mass connections, their component mass flow rate variables. Because of that, the software automatically sorts the equations and reduces the system to 2 equations and 4 variables. Again, we need to define still the same 2 variables to make the system well posed. So only thing we have to do is to select D and rho and move them to the constant box and get well posed system. So let's go to the model, select diameter and select density. As we can see, all equations are without the stars in front, and we have the sign that equation sorting and referencing is okay. If by any chance you have selected the wrong variable, you can always deselect and make another choice. So just again select, for example, rho or D, and then you're back to square one. So now you can again select them, but this is just for you to know this is reversible process, and you can change it until you are satisfied with your selections. Now let's move to the outlet connection. Here we have 1 equation and 2 variables. We know that the beta is the outlet flow coefficient and that beta is parameter, so just select beta. Beta will move to constants. Fm, component mass flow rate, will then be calculable, as also we have L origin, liquid level, a variable used from the origin system, which is buffer tank system, as if you remember we used or dot prefix to call this variable. Now each of our model objects is well posed, so if we go inlet connection, buffer tank system, and outlet connection, they're all well posed and solvable. Let's continue. Task number 8, initializing the buffer tank system. We have already explained model initialization and initialization procedure in Mobatec modeler in the second exercise. We will do the exact same thing here, but we will just take a closer look at the model initialization mathematical analysis of our model. This analysis is given in Mobatec modeler handbook, slide initial conditions. Here we can see all the variables that we have to give values at time 0. Known variables are the variables that we turned into parameters, so we know their value. And we have here the unknown ones, which must satisfy the model equations at time 0. First, let's enter parameter values into the model. Select the inlet connection, go to Parameters tab, and enter the values of alpha, fm, and xm. Alpha is 1 or 100%, you can change the unit here. Fm is 20 kilograms per second, and xm is also 1, which is 100% water. You can also change the units here. Now we can see that the parameter is checkmarked green. All parameter values you can find in Appendix 1, the table 4, at the end of the exercise. Now let's move to the buffer tank system. Select parameters. D is 0.15 meters and rho is 1000 kilograms per cubic meter. You can see the parameters are checkmarked green now. And we move to the outlet mass connection. Select parameters tab and enter value for beta, outlet flow rate coefficient, which is 20. Again, parameters will turn green. Now let's initialize all model objects. If we go back to the handbook, we can see the analysis of initial conditions of inlet mass connection. We have 2 equations and 2 variables, so we need no extra inputs to initial this model object. If we go back to the model and we select inlet connection, we go to initial values, just click calculate initial values, and we have initialized this model object, and the check mark is green next to the initial values. Now let's move to the buffer tank capacity system. Go to initial values and let's check the handbook again. Here we have the initial conditions analysis of the buffer tank capacity system. We have 5 initial variables and we have 4 equations. That means we need 1 extra equation in order to make this model well posed dynamically. So here we have component mass holdup change at time 0 and component mass holdup at time 0. So at time 1 second, if the integration step is 1 second, component mass holdup of 1 second will be component of mass holdup at 0 seconds plus change of component mass holdup at 0 seconds, and so on. So essentially we need to know the component mass holdup at time 0. And as 5th equation, in this case, we could define the value of component mass holdup itself, or the total mass holdup, or the liquid level at time 0, as software will use the equations to automatically back calculate the component mass holdup value. This extra equation we call initial condition, and in this case we decided to give the initial condition of the liquid level, which is 2 meters. So let's go back to the model. Here we have liquid level variable. Here we can enter 2 meters. And in order to state that this is initial condition, the fifth equation, just check the E box next to the L variable. Now we have stated that this is the initial condition for this system. Now just click calculate initial values, and now we have initialized buffer tank capacity system successfully. Now let's continue with the outlet mass flow connection. Again, let's check the handbook. We have one variable, one equation, so no extra inputs needed to initialize this model object. Let's go back, just go to Initial Values tab and click Calculate Initial Values. As you can see, we have initialized the outlet mass connection successfully as well. As you can see, initialization of mass connections is quite trivial thing, as they normally do not contain dynamic equations, differential equations. So once you initialize your systems, then you can immediately initialize all your connections. Here we have done all the steps one by one in each model object, but once you get up to speed, you can just select your model object, go to Equations tab, press Define Equations, open the big tab, define your equations, then immediately go to Equation Sorting, sort your equations, give them parameter values, initial values, and initialize your systems. And that will be a much faster way to do it. Let's continue. Task number 9. Running a dynamic simulation and monitoring variable values. To compile the entire model, make no selection or select the entire model. Both will work the same. Then go to Basic Commands tab and press Compile and go to Simulation button. You can find the very same button in the toolbar here, or press F12 on your keyboard. And now the model is successfully compiled and loaded into the simulation environment. Calculation step size is set to be 1 second by default, and if we want to have a real-time dynamic simulation, we'll have to give it 1000 milliseconds calculation delay. Dynamic simulation type is chosen and fixed step size integration method. Start the calculation by pressing Start Calculation button. Now you can follow the time, simulation time, here in the Basic Commands tab, or in the left bottom corner here. So now let's monitor some variable values. For example, let's select the buffer tank capacity system. In order to monitor variable values, go right click, go Show Table and choose Show Table 1. You can choose up to 5 different tables. Shortcut to get the table is to select the system and press 1 on your keyboard, or 2, 3, 4, or 5. So here it is, table number 1. These are the variables of the buffer tank capacity system. As you can see, you can resize the table like this. Here we have the updates of the every calculation step, and here are the values. You can also get this table, for example, for the inlet mass connection. Because we already opened the table, we can just select the mass connection, and then we will be able to see the variables of the mass connection, inlet mass connection. We can do the same for the outlet mass connection. If you want to permanently have variables of the inlet mass connection, for example, then you just have to click here and lock selection filter. Now we will always monitor the variables of the inlet mass connection with the table 1. Then if we need second table, just select the system, press number 2 on your keyboard, and we will get variable table 2. We can then lock that one, and for the outlet connection just press 3, and we can also lock that table as well. If you want to change some parameter values, for example the mass flow right in the inlet mask connection, go right click and go show parameter table. Again, we have 5 parameter tables, and you can also use the shortcut on your keyboard 6, 7, 8, 9 or 0 to open these tables. So here we open the parameters of the inlet mask connection, sorry. And now we can let's put it here. We can also lock this one. Now we can change this parameter from 20, let's say, to 30, and watch how other variables change. As you can see, the outlet connection will now reach 30 as well. Here's the update value, which goes down as the value approaches to 30. As you can see, it will become 30. Now we can stop the calculation. You could also make use of the table filters. For example, if you want to see only the total mass holdup in this table, here in the filter, before the star, just type the name of the variable and press enter. And now only the total mass holdup of the buffer tank will be displayed. The same applies, of course, for the parameters. For example, if you want to have only alpha, you just type A, and then the filter will leave only the variable which has A inside, which is alpha, so you don't have to type the entire name of the parameter. Okay, so let's move on to the next task. Let's close this variable tables. Even if you close them, if you want to see them again, you just have to press the shortcut button, so 1 for the first variable, and you will see the variable table 1. If you want to see the parameter table 1, press 6, and you will get again only alpha. So the selection that you have made before will stay with the tables. Let's continue. Task number 10. Adding variables and parameter displays. We have already explained how to make variable and parameter displays in the exercise 2, but we haven't explained how to make filled rectangle displays, and now I will make all the displays one by one. So let's go back to model. Go back to modeling environment by pressing mod button in the toolbar or F11 on your keyboard. Now we are in modeling environment. Just press V on your keyboard to add the value display, or go insert objects and choose value objects. Let's add one display here, and let's add one display here. From the first value object, I will make the total mass flow rate variable display. So description fin equals simulation variable is fin. Linked object, we'll just link it to the inlet mass connection. Okay. Engineering unit, kilograms per second. Number of decimals 2. Max value, let's say 50. Let's change the colors to some custom color, for example, green. And let's change the font color to, for example, also white. Just press apply. Now you can resize the value display object. I can also move this one a bit here, like this. Now we can reuse the made display to display the outlet flow rate. Here we will change to Fout. Simulation variable name is fm underscore h2o. For example, if you take a look in the outlet connection for the variable name, we will see, while in modeling environment, fm, then these square brackets, then h2o. But if you are in simulation environment and you want to see this variable, you will see that the variable name is fm underscore h2o. Then there is underscore for the name of the connection. But this is important, so the square brackets are turning into underscore h2o in the simulation environment, and we need to type the exact name of the variable in the simulation environment here. Now let's turn this display into a parameter value display for alpha. Here we will type alpha. Simulation variable name is alpha. Linked object is the inlet connection. Engineering unit percent. Here type 100% is maximum. Check allow value access in simulation environment, as we want to change the alpha value while running the simulation. And let's just check change, for example, the colors, the value object color to yellow, and font can stay black. Press apply. Here I will also add alpha equals, like this. Now let's reuse the parameter display, Ctrl C, Ctrl V, that we have made to make the parameter display for mass flow rate, which is user defined. And here we will change to fm equals fm user equals simulation variable is just fm. It is the same linked object. We will change unit to kilograms per second. Yeah, let's go 50 as well, and everything else is the same. Apply. Then you can resize a bit to get that everything can be seen clearly, and that's it. You also have the possibility to copy value display attributes. For example, let's add a new value display. Press V on your keyboard like this, and let's copy this value display attributes. Just select it, press Shift V, select the newly added display, and press V. As you can see, we have copied the attributes of this display. Now let's change this display settings to display beta outlet flow rate coefficient. Beta equals simulation variable beta. Linked object is outlet connection. Okay. The unit, enter the unit of beta. 50, let's go 100, why not? And press apply. Let's add one more display for liquid level. We can copy, for example, this display. Let's put it in the middle. Let's resize it. Select the display. Here we will type L equals, simulation variable is L, linked object is buffer capacity system, engineering unit meters. We can have 2 decimals, max value up to 10 meters, and here type uncheck allow value access in simulation environment, as this is variable, so we cannot change its value. It's going to be calculated. Check transparent to make the display transparent and press apply. As you can see, you'll get something like this, which looks nice. Now you can resize the display with your mouse. Like this. Now let's add the filled rectangle display to display the liquid level of this tank. So go and add empty display, just V on your keyboard. Right click to exit, select it, go to Properties tab. Here select filled rectangle display. Description is relevant now. Simulation variable is liquid level L. Linked object is buffer tank. That is correct. Max value 10 meters. Fill color, let's use blue. Value object color, let's use some dark gray. Okay, and press apply. Now you can resize the fill rectangle display the way that you like and place it where you like it. So let's make it like this. Okay, looks good. If you go to rectangle fill display properties, here you can see that the default orientation filling is from bottom to top, as we need here for the tank. But you can also choose to be top bottom or right left or left right, depending on your needs. Okay, so bottom to top, apply, okay. While in modeling environment, the displays will always display their maximal defined value. To use displays in simulation environment, we don't have to recompile the model, but just to go back to simulation environment by clicking Sim button in the toolbar. Now we are back to simulation environment again. Now let's start the simulation and let's play with the model parameters a bit. For example, let's change the FM user to 40 kilos per second, and we can observe that the level is increasing until the flow rate of the outlet connection becomes the same as the FM user. We will end up somewhere at 4 meters. We can now stop the simulation. Let's continue. At the very end of the exercise, you have some questions. Question number 1. What should be the beta value to achieve liquid levels of 4 and 6 meters in the tank? So let's find out. Let's lose the delay so that we can calculate faster. Start calculations. You can see now it is going much faster than the real time. Let's first go back to 20 kilos per second as it was originally, and we can see that 1 meter is the steady state liquid level of the buffer tank. Now let's change the beta from 20 to 10, and we will observe that our liquid level goes to 4 meters, so the answer is 10. Let's now find out what is the beta value for 6 meters level. If you go down, so 9, we need more, let's go 8, it's a bit too much, let's go 8, 15, and we get 6 meters level, so the answer is 8, 15. We can now stop the simulation. Let's continue. Question number 2. Make a cascade of 3 buffer tanks in series by copying and reconnecting model parts from the existing model. Rename the tanks to B1, B2, and B3, and rename the connections to B1, F out, B2, F out, and B3, F out. Tune the beta parameter value to obtain 6, 4, and 2 meters levels in the first, second, and third tank. Let's do it. Go back to modeling environment by pressing Mod button. Select the buffer tank. Copy. Right click, paste. Cut connections. And one more time, paste, cut connections. As we need 3 tanks. Delete the inlet connection, as we're not going to need it. Delete the sink, as we're not going to need it. Select the outlet connection of the first tank, press number 3 to add 2 more bending points. Connect and adjust so that it looks nice. Do the same for the second tank. Connect the outlet connection to the tank. Also add 3 bending points to make it look nice. Now you can adjust a bit the position of your displays, as they may move a bit once you copy your I'll just adjust them like this until I am satisfied with how they look. Okay, and here as well. Looks good. This is not a major issue. Okay, now let's rename the tanks. So this one will be B1, rename. This one will be B2. You can use F2 to rename objects. And this one will be B3, rename. This one will be fout underscore B1. This one will be fout underscore B2. And this one will be fout underscore B3. Now we are done with the topology. Close. Let's do it. Go back to modeling environment by pressing Mod button in the toolbar. Select buffer capacity system and the sync system. Right click, copy, paste, cut connections. And once more, right click, paste, cut connections. Like this. Delete the inlet connection as we are not going to need it, and the sync. Select the active point of the outlet connection, press 3 on your keyboard to add 2 more bending points. Reconnect the loose end of the connection to the tank. Do the same for the second tank. Delete the inlet connection, delete the sync, add 2 more bending points. Reconnect. Okay. Now if we select the first tank and press 7, we will see the name of the tank. We can do for the rest. We can see that we have the same name of all 3 tanks, and that is not possible. We have to have different given names. So let's press F2, the keyboard, and rename to B1, second one to B2, and the third tank to B3. We have to do the same thing for the outlet connections. So fout B1, fout B2, and fout B3. Okay. Now we can a bit adjust the displays, which moved once we copied the tank. That can happen. It's easy to adjust them back to their original positions. Let's do it here as well. Okay, this looks good. Now, as we modify the model, we have to recompile the model. You could save the previous model before you made changes by using Save As, and continue making the second model. Go to Compile and go to Simulation button to recompile the model. Yes, we want to discard the previous model. And our model is now compiled. Let's now start the simulation and see what are the values of beta parameters that we need to achieve 6, 4, and 2 meters in the first, second, and the third tank. Press Start Calculations button. For the 6 meter level, we already have that beta is 8.15. To obtain 4 meter level in the second tank, we also determined that we need beta to be 10. And in the third tank, we need to obtain 2 meters. So let's go 12. Okay, 13. A bit more, 14. And now we have 6, 4, and 2 meters liquid levels in the tanks 1, 2, and 3. We can now stop the simulation. This was all for the third exercise of Mobatec Model Introduction course, which was First Model Developer exercise. Until the next help video, stay dynamic. Bye.